Hello boys and girls, today we'll be learning about properties and structure, and this is the culmination of our bonding chapter or unit, whichever you want to call it. This is what we've been really looking forward to, because in biology you learned from Miss Reuter that structure determines function, and today we're going to focus on how the properties of the different types of compounds are based on how they're put together, their structure. We're going to look at each of the three different types of compounds, ionic, polar covalent, nonpolar covalent, and talk about how the structure gives that particular compound certain distinguishable properties. So let's start with ionic compounds. Remember, ionic compounds are formed when a metal transfers electrons to a nonmetal. And this is an important point that we remember about them, that ionic compounds form crystals, or sometimes you'll see it listed as a crystal lattice. If you just want to call them crystals, that's fine. So what does a crystal look like? Well, if we're talking sodium chloride, a crystal looks like this. It's a repetition of ions. Okay, so let's talk about this one and talk about what holds this together. What keeps these sodiums and these chlorides together? Well, it's the electrostatic attraction between the positives and negatives that holds this compound together, that holds those sodium and chloride ions together. This electrostatic attraction turns out to be between the ions, turns out to be extremely strong. And it makes sense. Whoops, I didn't spell extremely right. Extremely strong. It makes sense if you think about it, because if you think about how each one of these chlorides, each one of these chlorides is surrounded by 6 sodiums, and each sodium is surrounded by 6. So think about what that would do to the strength. They're really strongly locked into place. This is why they tend to be solids at room temperature. That doesn't mean always. Tend to be solids at room temperature. This is why they have high melting points. I'm going to go ahead and write out the word melting, even though I wasn't going to. In order to get this to melt, we have to break these bonds. We have to mess with the attraction these guys have for each other. And so it's a high melting point. That means it takes a lot of energy to melt an ionic compound. These guys tend to be brittle because these ions are held tightly in place. They're fixed. They don't want to move around a lot because of that strong interparticle force. I'm going to go back up here. Extremely strong. Inter means between. Particle means, well, particle. Interparticle force. Now I want to talk about their conductivities. These will not conduct as a solid. Conduct electricity. Will not conduct electricity as a solid. Why not, you ask? Tell your computer. Say to your computer, computer, why not? Well, the reason this is these ions are in fixed positions. In order for an ionic compound to conduct electricity, we have to have the ability for these ions to move. And if the ions can't move, then it cannot conduct electricity. So since these ions are in fixed positions, they're stuck in place by those strong interparticle forces, they can't conduct electricity. However, they will conduct as a liquid. Why? Because in a liquid, the particles are free to move around. And that's very important that you recognize right now that as a solid, an ionic compound won't conduct electricity because those ions are locked in position. But when we melt it as a liquid, when we make it a liquid, when we melt it, then those ions can move around. And if they can move around, they can conduct electricity. The actual mechanism they use to conduct, well, we don't really want to get into today, but just trust me, they can conduct when they're melted. So if you take some salt, put it on a burner, and melt it, which is very difficult because of the high melting point, it will conduct electricity when it's melted. I've not ever done it, and I don't intend to try it because of the high temperatures. These guys typically will dissolve in water. And this happens because we learn a rule. Here's the rule. The rule is like dissolves. We'll talk about it in class. I've got some cool demos. Like dissolves like. What that means is that polar compounds like to mix with polar compounds, and nonpolar compounds like to mix with nonpolar compounds. So water, as you well know, is polar, and an ionic compound is not polar, it's an ionic. But what happens is these ions, here's an ion, are attracted to the water molecules. See how this is a positive ion? The negative end of the water molecules, the negative end is by the oxygen, is attracted to that positive ion. See how they're arranging themselves like little soldiers, taking them somewhere? They're like, the water molecules are like bullies. They're like, hey, sodium, you're coming with us. Did you hear them? Those were real water molecules. That wasn't my voice. It was real water molecules here. And then the chloride ion, and sodium chloride is just an example. This works with any ionic compound. The chloride ion, the positive end of the water molecule is attracted. So the hydrogen end is the positive end. And so they surround the chloride. This is hard to draw. They surround the chloride and say, hey, chloride, you're coming with us. And this is a quick drawing of how ionic compounds dissolve in water. It's the attraction. This works because of the attraction between ions and charged ends of polar water. Whew, that was a mouthful. Attraction between ions and charged ends of polar water molecules. Remember that a water molecule has a positive end and a negative end. That's why we call it polar. It has poles. Okay, last thing about ionic compounds. I'm going to insert more writing space. The last thing I want to talk about in ionic compounds is conductivity when they're dissolved. They will conduct when dissolved in water. Why? Think back to why they would conduct when melted. Why will they conduct when dissolved in water? Because the ions are liberated. They're free. They're free. They're no longer stuck in those tight crystals. They're free to move around. And if the ions are free to move around, they're also free to carry charge, which allows the water molecule, the ionic compound and the water molecule, or the ionic compound in the water, to conduct electricity. So salt water conducts electricity pretty well. Cool? Cool. Let's move on to polar covalent compounds and talk about them in great detail. Okay, so remember with polar covalent compounds, these are formed with two nonmetals, two or more, I guess, in some cases, two or more nonmetals, and that they are sharing electrons. How do they share electrons in a polar compound? Unequally or unevenly is correct. So the electrons are distributed unevenly. And we've just been over how to do this a lot. So let's look at our favorite polar covalent compound, a water molecule. So I want to remind you that a water molecule, because this oxygen is very electronegative, ends up with a partial negative charge here and a partial positive charge there. And then this water molecule that's nearby also has a positive end and a negative. Here's our negative end and here's our positive end. And well, I haven't drawn it perfectly. I'm going to move it a little bit. That's so cool that I can move it. I'm going to move it to more like this. And you can see exactly what's happening right there, but we're going to talk about it. So the first thing we need to recognize about this is that when we're melting, boiling, doing all this stuff with this, we are not messing with this part. We are not breaking these bonds right now. This is extremely, very, 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 very strong. But we're not breaking these because right now we're working with only physical changes with these guys. When we start doing chemical reactions, then we're rearranging, we're breaking bonds and forming bonds. But right now, we're focusing really on physical changes because it's the physical changes that can give us information about the molecule itself. Now, between, I don't like the way this looks. Between these guys, between these two molecules, I'm going to change color there. Between these molecules, we are talking about this. This is called an intermolecular force. Now, earlier we called the force between ions interparticle, and now I'm calling it intermolecular because these guys are molecules. And you already know that covalent compounds form, form molecules. And this is what we're breaking during physical changes. We are breaking or fighting these IMFs, intermolecular forces, during physical changes. Now, there are types of intermolecular forces which I'd like to talk about. Well, I'll go ahead and list them now, but we need to talk about them in more detail later. There are 3 kinds of intermolecular forces. The 3 types of intermolecular forces are called hydrogen bonding, which is tricky because it's not really bonding; it's just attraction. There is dipole attraction, and there are something called London dispersion forces, which are a type of attraction, and we'll sum these up later on at the end. Right now, I don't want to go into great details on intermolecular forces, but those are the 3 types of IMF, intermolecular forces, that we are going to need to know. All right, so what's the deal here? The intermolecular forces, the IMFs, in all covalent compounds are weaker than the forces in the ionic compounds. Overall, in general, weaker, which gives them a lower melting point. Since they have lower melting points, they tend to be some solids, some liquids, and some gases at room temperature. So these are not like ionic compounds where the attraction between particles is very strong, so they're rigid. They tend to be solids at room temperature. These guys are a little bit weaker, easier to melt, and so they tend to be solids, liquids, and gases. And remember that lower melting point is because we have a weaker attraction between the molecules. Remember, we're talking about between molecules, intermolecular. Inter means between molecules. These guys do not conduct electricity. Yes, that's true, boys and girls. That means water does not conduct electricity. Pure water. When you think about tap water conducting electricity, you're thinking about a mixture. Tap water has other stuff in it. Or a bottle of Dasani, that water would conduct a little bit because it's got other stuff in it. Pure water does not conduct electricity because there are no ions. There are no charges to help move that energy through the solution or through the substance. These guys do exhibit an interesting property. When they're liquids, they exhibit a property called surface tension. And this surface tension happens because the little polar molecules, remember polar means having a positive end and a negative end, the polar molecules are attracted to each other somewhat. Think about this. If you had a box of magnets and you shook the box of magnets, the norths and the south ends of the magnets would all find each other and they'd stick together. And that's what the molecules of water do, and other polar covalent compounds. They are attracted to each other like magnets. Okay, this is going to be the end of part 1. Whoops, sorry about that. The end of part 1. Part 2 is coming up next. So I'm going to draw a line. Part 1.